The cosmic wonderland above our heads is filled with celestial bodies of all ages and shapes. However, we could never unveil its true mysteries, until now. The James Webb Space Telescope, often referred to as a cosmic time machine, has just discovered 33 teenage galaxies on the edge of our universe. On November 20, 2023, NASA revealed astonishing findings about these unexpectedly young galaxies, highlighting the presence of heavy metals within them and insights into the process of star formation. The James Webb Space Telescope is the most powerful spyglass of our age. Its main goal is to study the unseen infancy period of the universe, a phase we haven't visualized yet. Since it began operation in 2021, JWST has observed numerous distant galaxies, planetary features, comets, and more. Conceived and designed to help us understand the origins of galaxies, it's no surprise that JWST continues to challenge our understanding of the cosmos. By capturing celestial objects in infrared light beyond the visible spectrum, it has provided us with extraordinary views of galaxies billions of light-years away. As JWST looks back in time, it captures images of galaxies in their teenage years. Recently, it discovered 33 baby galaxies that appear relatively young compared to those we already know. But that's not the only groundbreaking revelation. These teenage galaxies contain heavy elements rarely found on celestial bodies so distant from Earth. The existence of these elements is puzzling due to their formation requiring multiple stellar life cycles, which implies the galaxies may be older than previously thought. This raises questions. What is the exact age of these galaxies? How far do they lie? Are they older than the Big Bang? What caused the existence of heavy metals in these galaxies? Electromagnetic radiation holds the key to answering these questions. By analyzing the redshift of these galaxies, scientists can determine their distance from Earth. Redshift acts like a cosmic fingerprint, showing how much a galaxy's light has shifted toward the red end of the spectrum due to the universe's expansion. To calculate the distance between galaxies, astronomers also rely on properties like the Hubble constant, which describes how fast the universe is expanding. Understanding the formation of such distant galaxies requires us to consider the bigger picture framed by the Big Bang theory. This renowned cosmological theory suggests the universe began 13.7 billion years ago with an explosive event. Stars ignited and galaxies slowly formed. Over cosmic time, the universe itself functions as a time machine, enabling us to observe distant galaxies as they appeared billions of years ago. For nearby galaxies like Andromeda, light takes only a few hundred to several million years to reach us, meaning changes within such timescales are minimal. However, when we observe galaxies billions of light-years away, we're peering into a time when the universe was in its infancy. For example, observing light from an object emitted 6 billion years ago shows us the universe when it was about 8 billion years old. Observing light that began its journey 13 billion years ago reveals the universe less than a billion years old. The James Webb Space Telescope's recent observations challenge some aspects of the Big Bang hypothesis. The galaxies JWST captured appear too small, old, and smooth compared to expectations based on universal expansion. Big Bang theorists anticipated that galaxies in such a young universe would appear larger and more irregular due to the expansion. However, JWST images show these galaxies as surprisingly smooth and compact. As the universe expanded and cooled, transformations shaped matter's formation. During the first moments after the Big Bang, a process called nucleosynthesis led to the creation of lightweight elements like hydrogen and helium. Extreme conditions during this phase allowed protons and neutrons to fuse, forming simple atomic building blocks. Hydrogen, the most abundant element, and helium, the second most abundant, were created during this time. These elements, observed in galaxies formed long after the Big Bang, add another layer of complexity to the JWST discoveries. A recent study published on November 20, 2023, revealed new insights about these teenage galaxies, highlighting details about their redshift and spectrum that are reshaping our understanding of cosmic history. They measured the distance using the speed of light as their trusty guide, allowing them to determine precisely how far back in time they are seeing these galaxies. Similarly, a group of scientists from Northwestern University used NASA's James Webb Space Telescope, JWST, to study the chemistry of distant galaxies. Led by Stum and Rudy, the project, known as Cecilia, Chemical Evolution Constrained Using Ionized Lines in the Interstellar Auroral Survey, paid tribute to Cecilia Panga-Poshkin, one of the earliest women to earn a PhD in astronomy. She was also the first astronomer to determine that the Sun's chemistry differed from Earth's and that the Sun and stars like it are primarily composed of hydrogen and helium. This study focused on how JWST provides new and detailed measurements of the spectra of distant galaxies, referred to as teenage galaxies, based on their developmental stage. These galaxies were not in their infancy when they emitted the light that we now see, but rather were experiencing a significant growth spurt, actively forming numerous stars. The study explained the program design of JWST, including the required exposure times and the setup of the multi-object spectrograph. It involved deep observations of star-forming galaxies at specific redshifts and processed the data using a pipeline called JBST. The early findings revealed that teenage galaxies, born 2 to 3 billion years after the Big Bang, are surprisingly hot and contain unexpected elements like nickel, making them challenging to observe. Carnegie astronomer Alison Stumm emphasized that understanding the chemistry of these galaxies provides remarkable insights into the early years of our universe. All elements heavier than hydrogen and helium on the periodic table are produced during the life cycles of stars. The Cecilia survey examined the line spectra of distant galaxies to understand their growth and future evolution, focusing on their teenage years, a critical developmental phase. The spectra revealed elements like oxygen and sulfur, offering insights into a galaxy's past and future activities. This research helps astrophysicists explore why some galaxies become red and dead, ceasing star formation, while others, like the Milky Way, continue forming stars. When scientists analyze a galaxy's spectrum, it serves as a chemical fingerprint, revealing its elements and placing it within the universe's expansion model. Stumm and her collaborators used JWST to observe 33 distant teenage galaxies for 30 continuous hours during the past summer. They combined light from 23 faraway galaxies and marked them with red rectangles in the Space Telescope images, detecting faint emissions from 8 specific elements: hydrogen, helium, nitrogen, oxygen, silicon, sulfur, argon, and nickel. Stars create all elements heavier than hydrogen and helium. These elements weren't present at the universe's beginning. Stars had to forge them internally. When light from these galaxies first shone, numerous stars had already been born, lived, and died, spreading new elements through supernova explosions. This process occurred even before the universe reached 1 billion years in age. The existence of these elements suggests extensive star formation and supernova activity in these galaxies, potentially indicating they are much older than the Big Bang hypothesis suggests. Notably, the discovery of nickel surprised astrophysicists. Nickel is heavier than iron and rarely observed, even in nearby galaxies, due to the specific conditions required for visibility. Its presence in the spectra of these teenage galaxies implies unique characteristics in the stars forming within them. These galaxies are also surprisingly hot, with temperatures exceeding 1,350 degrees Celsius (2,462 degrees Fahrenheit), far hotter than the hottest regions in regular galaxies. Stumm explained that this high temperature reflects a unique chemical composition, as gas temperature and chemistry are interconnected. The glowing nickel in these galaxies indicates extreme heat in star nurseries. Despite having fewer stars than the Milky Way, these galaxies possess a higher proportion of very hot stars. While we understand the general process of galaxy formation, the specific physics behind these differences remain elusive. Stumm suggested these galaxies are in a chemically immature state, undergoing rapid development. This research is part of a planned series of 7 or 8 studies. The next study will examine the light spectra from a single distant galaxy, offering even deeper insights into galaxy evolution. Stay tuned for more revelations.